this video, we discuss the process of choosing the most suitable model for your research question. For this video, we will focus exclusively on zero-dimensional, 0D models. When you are modeling an aquatic system, the degree of model resolution, both spatial and temporal, is dependent on your case study situation, including the shape and size of the environment you are modeling and the scale of your research question. Furthermore, the level of detail that is required to accurately model your aquatic system is a key factor in your choice. The changes occurring in aquatic systems are functions of time and space. Then, for example, if the desired timescale of the research question is long enough, the system will have enough time to homogenize in space, and there is no need for high spatial resolution. To justify the resolution of your model, you need to answer questions such as: are you focusing on the behavior of the whole system or the behavior of the individual parts of a system? Are you evaluating the short-term behavior and the responses of a system to stressors, or are you hoping to gain insights into the long-term behavior of a system? What level of spatial, temporal, and biogeochemical details are required to address the specific research question? The right spatial and temporal resolution for your model should be a balance between the scale of your question and the level of detail that is required to address that question. To provide short-term weather forecasting, we use complex models with a high level of detail. These details allow us to model the physical laws that govern the atmosphere. These models start the simulation based on our knowledge about the current weather conditions, what we call initial conditions. These conditions can be fed into supercomputers that can simulate the atmosphere's evolution in the next few hours or days and predict many atmospheric variables, such as temperature, wind, rainfall, and pressure. The weather forecasting process performed by numerical models includes significant amounts of computing and data processing. These models are usually run a few times every day. In contrast to short-term forecast models, we have simpler models that are usually used to simulate the aggregate behavior of systems over the long term, and which do not focus on the behavior of their individual parts. They are usually used to address big-picture questions. For example, in research on the Mediterranean Sea with a box model approach, researchers answered questions such as: how have humans modified nutrient cycling in the Mediterranean Sea since 1950? How will climate change impact biogeochemical cycling in the Mediterranean Sea? These models have fewer data requirements and reduced computational complexity in terms of physical dimensionality, and are helpful in providing long-term predictions of a system's responses to stressors. Let's start with the simplest model. For example, we can consider a shallow lake in fall as being similar to a bucket of water. The volume of this bucket/box is equal to the volume of the lake. Imagine you are simulating dissolved oxygen concentrations in this lake. We can assume that the whole lake or bucket is fully mixed due to wind and temperature effects. Therefore, because the lake is fully mixed, the concentrations of dissolved oxygen, or DO for short, are the same throughout the lake in each snapshot over time. In this case, we do not have spatial resolution for the lake or bucket, and the amount of DO concentration only changes over time, making it a zero-dimensional environment. Note that the concentrations, or mass of DO in the lake, may change in time based on the oxygen supplied to the lake from tributaries or atmospheric exchange, and the oxygen that leaves the lake from the outlet of the lake. The DO concentration also changes due to biogeochemical processes inside the lake that consume and produce oxygen. Keep in mind how the mass and concentration are related. Concentration is equal to the mass of the solute divided by the mass of the solvent, here water. For simplicity, we assume that water is incompressible. It is actually a bit compressible, so the mass of the unit volume of water is constant. Therefore, we define concentration as mass of solute divided by volume of water. The units for concentration can be in grams per liter. Based on the law of conservation of mass, the net change in concentrations of any water quality variable in a lake or box over time would be equal to the sum of the input fluxes minus the outflow fluxes minus or plus other processes that consume or produce the desired water quality variable. In this case, based on the time resolution you pick for your modeling, your model's result will be a time series that represents the DO concentrations in the lake over time. Remember that the changes in concentration over time can be true for all water quality variables, like phosphate, nitrate, or others. The only thing that differs between them is the biogeochemical processes happening inside the lake, which are specific to each variable. Box models have long been used to analyze the annual budgets of nutrients. For example, let's look at the annual budget of total phosphorus, TP for short, of the western basin of Lake Erie using this approach. This basin is shallow, and at the annual scale, we can assume that its contents are fully mixed. Some of the input fluxes to this basin include those from wastewater treatment plants, inflows from the Detroit River, and other tributaries such as the Maumee River, as well as atmospheric depositions. We can imagine the western basin as a box. In this basin, the water moves mainly from the west toward the central basin. The flow of water is influenced by discharge from the Detroit River, which pushes the water eastward. Moreover, the burial of TP in sediments also occurs in this basin. In the case of TP, we use the equation that shows how the concentrations of TP change in the western basin of Lake Erie over time. That is, first calculate the sum of the input fluxes and the output fluxes. Then, subtract the sum of the output fluxes from the sum of the input fluxes. Finally, calculate the net burial flux that removes TP from the water column and add them to the sediments. In the model, the net burial flux can be explained as a first-order rate constant multiplied by the concentration of TP in the lake. As you include these processes in your model, you have to provide estimations of parameters, in this case K, to your model. The units for the fluxes are written as a concentration over time, for instance, grams per liter per year. If you are interested in analyzing the budget of phosphorus species, you may break down the TP in this basin into dissolved inorganic phosphorus, or DIP, dissolved organic phosphorus, or DOP, and particulate organic phosphorus, or POP. Now, in addition to inputs and outputs, you have to add the internal processes that occur between these species. This model can then provide more insights into species and the processes inside the lake. But to get that information, you will have to provide more information to the model as well. For example, you have to provide all of the input and output information on each species, as well as proper representation of each process in the model. Thus, you have to deal with more parameters. Note that we still do not have spatial resolution, just the DIP, DOP, and POP concentrations for the whole basin and their changes over time, making this a zero-dimensional model. In terms of complexity, regardless of the dimensionality, we can have a very simple or very complex box model. As we include more species and processes in the model, we add to its complexity. Let's see what questions you can and cannot answer with this model. Can you simulate how the average annual concentrations of DOP in the whole basin will change in 2 years if you reduce the DIP inputs from rivers by 10%? Yes, you can. Can you calculate the average monthly concentrations of DIP in the bottom water of the lake in August? No, the whole DIP in the lake is represented as one box, so we do not have the spatial resolution that is representative of the bottom of the lake. And now, to sum up what we have learned in this video. To find the right model to answer your question, you must ask yourself the following. Are you focusing on the behavior of the whole system or on the behavior of the individual parts of a system? Are you evaluating the short-term behavior and responses of a system to stressors, or are you hoping to gain insights into the long-term behavior of a system? What level of spatial, temporal, and biogeochemical details are required to address the specific research question? We brought several examples that help you gain insights into how to choose the right model. You saw that, for example, 0D models are a good choice for analyzing the loading budgets in aquatic systems.